I am very happy to introduce Fredrik Johansson,
Yep.
who is coming to us from MIT, where he's a postdoc in David Sontag's group. He has been doing a lot of very interesting work at the forefront of machine learning and causal inference, and I'm very much looking forward to hearing the talk.
Thank you so much. Thank you so much. Great to be here. Yeah, so for the last couple of years, I've been thinking a lot about causal effects, and the biggest reason for that is that I'm working in something called the clinical machine learning group at MIT, and almost all of the problems that we work with some exceptions, are inspired in some way by healthcare. So just I'll go through a few examples of what that might mean. One of the first problems that David worked on in his lab was predicting diabetes onset. And as you know, that diabetes is a very large problem here in the United States in particular, but elsewhere as well. And this is your standard sort of prediction problem. You want to figure out what is the risk of a person developing type 2 diabetes. So what they did in this work, wasn't in part of this, but essentially look at the person's health record or insurance record and find predictors or symptoms, features that are predictive of the risk of developing type 2 diabetes. So the question here is essentially, who is at risk? Who should we think about perhaps intervening on or treating differently? A more recent problem that I'm thinking about is opioid addiction, which is very relevant on the East Coast. I don't know anything about opioid addiction on the West Coast, but it's a very big problem in the States as well. And essentially what we want to figure out here is what about the healthcare system, or what about the way that we are prescribing opioids now is driving addiction, essentially. Over 10,000 people every year die from overdoses related to prescription opioids. So these are not drugs from the street. There are potentially overdoses that we could prevent. And people need pain medication, but in a lot of cases we could prescribe less. So we know simple things like larger subscriptions mean high risk of developing addiction. That's very reasonable, but perhaps we can figure out other reasons for or other sort of drivers of this. And lastly, I'll mention sepsis management, which is something that a lot of people in the machine learning community have looked at when it comes to sort of healthcare tasks. And sepsis is one of the leading causes of death in the intensive care unit. And it's a complication of an infection. So essentially, you can have really horrible complications such as organ failure, etc. And one of the first things you should do, obviously, when it comes to an infection is to treat the infection. But a lot of the things that we do when we treat patients with sepsis is also just management. Things like the blood pressure, the heart rate, the oxygen intake can all be affected by this. And this is a sort of more continuous task of managing patients. We have to make sure that all these things are in the right range. So for example, if your oxygen drops too low, you might want to put the patient on a mechanical ventilator. And if you do that, you might want to sedate the patient, et cetera, et cetera. So this is more of a sort of sequential process. And we want to manage these patients so that their long-term quality of life is good, as opposed to just making them survive the first 24, 48 hours or whatever they spend in the ICU. Because a lot of the sort of interventions that we do have long-term effects. So these three problems illustrate essentially like three different modes of applying machine learning in healthcare. And the first one being a very standard prediction problem that I'm sure most of you have worked with a lot. And essentially figuring out who's at risk of diabetes onset is something that we can do using just supervised learning or prediction-like methods. But the second one, figuring out what are the drivers of opioid medication and how can we prescribe opioids differently so that we reduce the risk of developing addiction. That's more of the sort of causal problems that I will be focusing on today. Essentially, we might be able to, or we might consider choosing between a synthetic and a natural opioid. I shouldn't say medication, but and we're interested in what is the contrast between the responses under these two choices of medication. And the last one is more of a sequential decision-making problem, or a reinforcement learning problem if we want to treat it like that. But we make a series of choices where each choice depends on the previous choices, but also what happened as a result of them. And This we can think of this as a slightly more complicated version of this in a lot of cases, but we are also interested in a slightly different quantity. We want to figure out what is a good policy, a good reactive policy for if we see a patient in a certain state, what should we do? Which is slightly different from this, in which we might consider, if I choose between these two things for everyone in the population, what would happen? Whereas in the policy setting, we might not consider the whole range of actions for everyone. So the sort of broad theme of this talk will be to predict effects of decisions. And we need somehow causal reasoning to do this. This is what I will argue, and I'm sure you've heard this argument before from others here. The main thing that I've been thinking a lot about recently is that we have a lot of high-dimensional data in healthcare, and it's not only because of the sequential problem, but also the fact that we have, diagnosis information, we have other kinds of medical history, and we have a bunch of symptoms. We have genetic information in some cases. We have X-rays. A lot of things that contribute to a high-dimensional data regime. And then the second part of this talk will be essentially linking this to domain adaptation, which is something that I've done successfully in the past. Domain adaptation, if you know, is part of transfer learning or an instance of transfer learning. It has a lot of similarities with causal effect estimation. So the last part is kind of an open question, but I recently I was working on a project of essentially trying to figure out what will go wrong if we apply something like reinforcement learning without thinking too much in a healthcare problem. And specifically, I will be talking constantly about what's called off policy or observational settings where we can't run an experiment, essentially. So in those settings, what should we sort of try to figure out about our policies before we apply them in practice? So the types of problems that we think most about in our group is something like this, or at least I do. There's a lot of work on sequential things as well, but we'll get there a bit later. So we can imagine a patient coming into the hospital. She's 54 years old and female, and she has high blood sugar. So this could be a pre-diabetic patient. We have to figure out how can we manage her blood sugar so that it's lower a few months down the line. And we can consider choosing between two different medications to do so. And the question then is, a few months down the line, which of these medications will have a better effect on her blood sugar? And these will be what we call the potential outcomes of this choice. So I will denote here by Y0 the outcome that we observe if we were to give medication A, and Y1 the opposite, or the outcome under medication B. So in a lot of cases, we could perform an experiment to try and figure this out. We can gather a bunch of pre-diabetic patients and then test these two medications separately and figure out what was the sort of average response or even conditional response in these groups. But for a lot of cases, we can't do that. And it could be because the patient groups are hard, or the patients are hard to recruit, or it might be expensive. But there are also some types of interventions that we just can't randomize, like forcing patients to smoke to see the effect of that, etc. So the typical data set we will be thinking about is something like this. We have some descriptors about the patient, like their age and blood pressure, etc. And we have essentially a column recording which treatment they received previously. We know what their blood sugar was a few months down the line. We want to figure out what among these choices of treatment was the better one. The problem, of course, is that we can only observe the outcome under one of these treatments. So what we would like is essentially to fill in these missing cells in this table. And crucially, these cells are not missing at random. Yep.
In this example, do we also know their pre-treatment blood sugar?
Yeah, that can be, exactly. That's. Oh, sorry. Yeah. So the question was, do we also need do we also know the blood sugar prior to treatment? And yeah, that would be a good feature to collect for sure. Yeah. So essentially, this slide is meant to argue that, or meant to illustrate that these cells that we want to fill in, we can't treat them as the standard prediction problem in the sense that they're not missing at random. observations that we have are not representative of the observations that we want necessarily. So that will be the goal of this talk, to figure them out. So I'll introduce some notation to talk about these things, and the first being X, a big feature vector essentially, or a covariate representation. This could be an image. This could be some insurance claim information. We have treatment assignments T, which I'll for the majority of the talk I'll assume is binary, a choice of A or B. And we have potential outcomes under these two different treatments. This will be Y0 and Y1. And our goal is to figure out the outcome under an intervention for a specific patient X, or a patient represented by feature X, or the difference between two interventions, or the outcomes under two interventions. So I think it's easier if I just show what I mean in terms, or using a figure. So this here could be the outcome under the first intervention, the control outcome, if you like. A function of X, for example, age, and I put mortality on the x-axis here. It's likely that you're more at risk of death when you're older. The question is, can we use a treatment to sort of reduce this risk of mortality? And that might be the case. We can have a function that represents the outcome under treatment that looks something like this. These are just invented, but this is not unreasonable to assume. So if you're at high enough age, there's nothing we can do, but perhaps in the sort of middle region here, the treatment has some effect. So what you can see is essentially a couple of things. The effect of choosing the treatment 1 over treatment 0 seems to have an effect in some regions, but not in all. So we have what's called a heterogeneous treatment effect. But also it seems to be mostly sort of beneficial, the treatment. Like this difference between these two lines, which is what we're interested in, is mostly negative. So you reduce the mortality if you choose treatment 1. Now, of course, we don't observe these lines, right? These curves are the goal with the study. Those are what we want to find out. But we observe only a skewed sample of these curves. This is what it's illustrated with a table before. And we might have a situation something like this, where we have a treated group. These should be 0 and 1 and not 1 and 0, by the way. A treated group that's a little skewed to the older population here, that you're more likely to receive treatment if you're older, and a control group which is younger. And even worse than this, we don't observe the curves in the support of these densities either. We observe samples from these densities, right? So essentially, we might see something like this, where we have a bunch of younger patients that didn't receive treatment. These are the blue dots here following the solid curve. And we have a bunch of treated patients that are a little bit older. And if you look now at the average response to treatment, or the average outcome in these two different groups, we see essentially that the average for the treated population is higher and the average for the control population is lower. But what we concluded before was that the treatment was always beneficial. So it's kind of surprising, or not if you've seen an example like this before, but it's what you can see is essentially that these averages do not tell the story that we're interested in. Because here it appears that the effect tau, or the difference between these two outcomes, is adverse on average as opposed to beneficial. And of course, this is an instance of confounding. This is age here influences not only the response to treatment, but also the treatment itself. Okay, so we have two problems, essentially, as far as I'm concerned. We have confounding, which is what I just illustrated, that if we look at just the sample averages that we received, we get the wrong idea of the effect. But we also have an overlap problem, which I didn't talk too much about before, but you can see that these two groups are essentially disjoint. And we have to work with that somehow. And the typical way to solve these problems in causal inference, at least papers, I hope not in practice, is to assume that these do not exist, these two problems. And this is, we'll talk a lot about this going forward, but essentially the first assumption that people tend to make in these kind of situations is something called ignorability, in which you assume that if you know X, if you know what caused if you have enough variables to predict essentially the treatment assignment well, the two potential outcomes that you are interested in should be independent of that treatment. So if we control for x, we can estimate the effect tau. The other one is common support, saying essentially that at any point along the axis that I showed before, or any point in the covariate space, we have some probability of receiving any of the treatments. So if we want to compare the difference between two treatments, or the outcomes under two treatments, we would need, of course, to have samples from each. And this is what I'll talk most about, I think, today. There are more assumptions that you need, like IID assumptions is one of them, and this consistency is another. This saying essentially that if you prescribe treatment T, you will observe the outcome under that treatment. And this is not always true. If a patient elects not to take the treatment you prescribed, then you're not going to see that outcome clearly. But I will take this for granted for now, and I'll talk about the other ones. Okay. So we still have observed confounding. We still have variables x that we need to control for. So roughly speaking, what we would like is to figure out what is the observed outcome under treatment for a patient X, but we only have this function for the people who already received that treatment. We only see the outcome under treatment for the treated. So how do we connect these two? Well, there are a couple of different solutions to that. Essentially, if you have the two conditions that I showed before, there are a suite of methods that you can apply to cross this sort of divide. And three of the most classical ones are these. Regression essentially fits a function to each potential outcome or each observed outcome under each treatment. And reweighting, I'm sure you've seen before in other contexts if you haven't in this, essentially doing importance sampling to figure out what is the, how do we find a representative sample of the whole population from the bias sample that we have, matching, just pairing up essentially people with similar covariates to figure out what would be their counterfactual outcome if they had the opposite treatment. So I will talk mostly about regression estimators today, and under the two assumptions that we had before, we only have to do regression to solve our problem, with some caveats in the sense that we might not have the amount of samples that we need. But essentially, under those conditions, you get that the potential outcome under a certain treatment is equal to the sort of conditional outcome. And this is you can do this in a lot of different ways. You can solve these kinds of regression problems in a lot of different ways. The most simple one, or the most perhaps intuitive for someone who comes from a machine learning background, is to treat these two curves as two different prediction problems to solve, or two different estimation problems. So you can try and fit the blue curve separately and the orange curve separately, and take or construct their difference to get your prediction. But there are also methods specifically designed to estimate the difference at once and not solve the two prediction problems. But our problem remains that if our two treatment groups are very different, for example, if we didn't have overlap, solving these estimation problems is not going to be easy. At least in the sense that we're not going to be able to, the error that we have on the data that we observed is not going to be representative of the error that we expect on a different, or counterfactual intervention, if you like, where we assign the opposite treatment. So there are a few different problems that make this hard, and the most relevant to this talk is that we have often high-dimensional data. So there are essentially two aspects of this that have basically the opposite conclusions. One is this idea that if we measure more variables, we're less likely to have left out something that we need to adjust for confounding. And this is true, but I put an asterisk here in the sense that we're not guaranteed to have less bias necessarily if we include more variables. This is a little technical, but you can show essentially that if you include variables that you shouldn't have, you will introduce more bias than if you left them out. And the most famous example of that, I think, is M-bias, which is, I'm not going to get into what that is exactly. But another one would be where you condition on a variable that happened as a result of treatment or after treatment as opposed to before. So you can introduce selection bias and that kind of thing. But this, I'm sure you're much more aware of all the time, because whenever we have high dimensionality, we have to struggle with sample sizes. In this case, we also have a different kind of curse of high dimensionality, in the sense that it's less likely that our two treatment groups overlap, as we call it, when we have more variables. So if you think about the matching problem that I flashed before, if you want to find someone who's very similar to you but had the opposite treatment, that gets less and less likely the more variables you have. Or said differently, you could say that everyone becomes roughly equally comparable when you have a lot of data, or a lot of dimensions, I should say, which is not what we want. So the question then is, how do we mitigate this curse of dimensionality? And specifically what I've been thinking about is, can we learn a representation, or can we find a representation of our data, phi, such that we still have the two assumptions that we needed for estimating causal effects. We still need ignorability. We need to adjust for confounding. And we also need common support, of course. But if we find a representation that's smaller than our original space, there's a chance that we can sort of bump up the margins on this a little bit. We can find better support or better overlap than what we had before. So if you think of this as being, a large number of covariates, for example, that we want to adjust for, just removing some of the variables would be the easiest way to achieve this. We have a better chance of having overlap. So I've thought about this problem for a while. A few years ago, I started working on this, and what we did essentially at that point was to start and draw comparisons between causal effect estimation and domain adaptation.
So,
yep, go ahead.
Just for intuition,
yep.
Is there, I don't know, like a quick illustrative example to see how phi-effects might help with ignorability? Like in your mortality example, I could see that, okay, maybe you start discretizing age or something, right? And then you obviously get better overlap.
Mm-hmm. So the question was, is there an example that illustrates how phi can be useful for ignorability or helpful? And it's the opposite. Like whenever we remove information, it's less likely that this will hold, except for the biases that I mentioned before. So that is actually the problem. Like we want to find phi to achieve this, but this is the constraint that we have essentially.
So effectively, if I did not have, so let me think about not having pathological things that are maybe increasing bias.
Yep.
Then would I effectively be asking what is the largest, like X should more or less satisfy ignorability already, and just asking what is the largest phi I can work with while getting common support, or good enough.
Yeah. So the question again for the recording is. Oh man, sorry, I wish I could repeat that back. Yeah, should I be thinking essentially, should I try and get the largest phi so that I have common support, or better chance of getting common support, but so that I still believe that I have ignorability? Yeah, I think that's a reasonable way to think about it. This will be a trade-off for sure. Like essentially, you can think of this as variance and this as bias, right? And in some cases, you might have an easier time achieving this than you might that. So you might be more concerned about keeping information than removing it. I don't have a great general answer to that question, but I think that's a reasonable approach to take. Maybe after we see some algorithm or theory, that you might have a better idea of that. I hope that's the case. So we started thinking about domain adaptation because it turns out it's very similar to what I'm talking about, and I used to just say what I learned from domain adaptation here, but essentially I've changed my mind a lot on the topic of domain adaptation too, working with this problem. So we will consider just one side of the causal effect estimation problem from before, and essentially we would try and predict this this blue curve, or this outcome under control medication for the treated population. So for the red points, we want to infer what is their sort of location on the blue curve. And doing this one-sided problem, or solving that one-sided problem, turns out to be the same as doing what's called unsupervised domain adaptation. And in that specific formulation, so like domain adaptation is essentially the idea that you want to learn a model or fit a model on one type of data and then apply it to something else, or one distribution of data and apply it somewhere else. And what the data that you have essentially in the specifically unsupervised domain adaptation formulation is labels from what's called a source domain and features from that domain, and then you have only features from another domain called the target domain. So you have features and labels from the source and only features from the target. So these map to counterfactual prediction in the sense that these are your factual control outcomes, the outcomes that you observe, and you have your treated group but not treated labels, essentially, based on the slide that I showed a minute ago. And your goal is to figure out the labels for the unlabeled group. The assumptions are very similar in these two problems, the counterfactual prediction and domain adaptation, in the sense that we have this ignorability condition still that I showed before, but it would be called something like covariate shift in domain adaptation. It's usually written slightly differently, but the idea is essentially that the labeling function that we want to learn and apply in a different context doesn't change between domains. So P of y given x, if you like, is fixed when we go from one domain to the next. And one of the most often considered tasks in domain adaptation, at least when it comes to the machine learning community, is is image classification, essentially. This is a benchmark that people are very comfortable with. And these illustrate two different benchmark problems that are often used. Here on the top row we see, well, I don't know if you can see it, but it's digits from house numbers that have been cropped. So this is essentially the center digit is the label of the image, so 7, 3, and 0, I think. And the bottom row here is the MNIST that you've seen a million times. But what's happening here is essentially that we use these images for learning, and we want to predict the labels of these images in the bottom. And a domain adaptation algorithm, where a suite of domain adaptation algorithms achieve an accuracy on MNIST of about 80% or so, having learned only from these SVHN digits. And the random guess would be a lot worse than that, 10% or so. So something seems to be working here. But what you can also see is that these two densities, or these two classes of digits or images do not overlap at all. There's measure 0 for the house numbers in this set. So how does that work? We're extrapolating essentially, wildly. We're extrapolating to somewhere we don't have any data. And in this example, you can see perhaps a bit better why this might work, in the sense that these are synthetic street signs and these are real ones. And I mean, they look similar, right? I mean, they have done a decent job synthesizing street signs, but still we don't have overlap in the strict sense of the word. So, okay, if we want to make if we want to connect domain adaptation to causal effect estimation, when can we expect a similar performance for estimating causal effects? When can we expect to do that, even though we don't have overlap?
Question?
Yep.
So I guess when you showed your corresponding quantities in domain adaptation and
Yep.
factual inference, one thing that was maybe missing for me was hypothesis class.
Yep.
Right.
I will get to that. Yeah.
Okay.
Exactly. So I'll take the sort of machine learning view of things now and think about risk minimization. So I won't assume that I have the right model. Yep. I didn't repeat that question, by the way. He was asking if I think about the hypothesis class essentially when it comes to causal effect estimation, and yes. Mm-hmm.
For the common overlap, should I be thinking of the probabilities as being estimated, or this is like the ground truth for the data generating process?
Sorry, repeat the first part of that.
For the common overlap
Oh.
assumption,
Yeah.
is this a statement that we are making about the data generating
Mm.
distribution, or is it a thing that we are like estimating and trying to stay away from the extreme?
So the question is, for the overlap condition, should I think about those as being estimated densities or sort of the problem, the data generating process? And for now, we can think about it as the data generating process. But whenever we do something that relies on knowing them, obviously we will have to estimate them in practice typically. So if you compare to, I will not assume that we know, say, a policy for treatment.
I think I'm just getting tripped up when I'm learning the representations phi.
Mm-hmm.
How am I assuming that interfaces with this data generating process that may have no knowledge of what phi I come up with?
Yes. So the question is, if the fee is invented by the practitioner or whatever, how can I connect that to the assumptions that I make about the data? And we will see why that can be a problem later. Yeah, I'll come back to that. So the risk that we would like to minimize now, for the purposes of this sort of part of the talk, is essentially the risk in predicting the control outcome. So that's F0 would be our hypothesis for the control outcome for the treated groups. I have a 1 here. So R1 F0 is the risk for the control outcome for the treated. And essentially this is just what you expect, the expected loss under the assignment for the treatment group. And the loss can be something like the squared loss or the 0-1 loss, etc. And if you do have overlap, a way to get a consistent estimator of this quantity would be to use importance weights, where you take your empirical risk and essentially just reweight each sample by the ratio of its likelihood under the treated and the control groups. But as we don't have overlap, we can't do this because P0 might be 0 somewhere. So we don't expect to have good overlap in high dimensions. And even if we did in some sort of extreme sense or in some theoretical sense, this estimator would have a very high variance. So we're not going to do importance weighting here. So what we can do is to take some inspiration then from domain adaptation, and we can try and bound the risk instead of trying to estimate it using importance weighting. So we're not necessarily going to have a consistent estimator in the classical sense, but at least we can figure out maybe something about how poorly we're doing, or get at least a direction in which to optimize. So if we have ignorability with respect to the variables x, we can write a bound in the following way, where we say that the counterfactual risk, or the risk that we defined on the previous slide, is bounded by the factual risk. So this is how poorly are we fitting the curve, the blue curve, for the blue points. And this here measures essentially how different can two extrapolations be in your hypothesis class H to the treated group. So it's defined here. And this is an integral probability metric, or an IPM. There are other formulations of this as well. The one bound due to Ben David looks at something called the H delta H distance, and the H distance. There are a few different formulations of this, but they have a very similar shape. Essentially, you're looking at how large can the difference be between the expectation of some function evaluated over P and evaluated over Q. So this is now saying, as long as the loss function, the loss at a point x, lives in this space H, this bound is correct.
Sorry, it should
Yep.
be the composition of the loss with something from the class like F is controlled.
So actually, yeah. So I'm glossing over some details here, but the condition that's necessary is that the loss of f for any f is in here, is in H. So there's another formulation where you get an additional term due to the triangle inequality, essentially, where you have the realizability of the label in H. Okay, so people wrote down a lot of these types of bounds over the last 10 years, and what came out of that was essentially a suite of algorithms that attempt to learn a space where this is made small, but we can still do good prediction. Okay, so the goal was to minimize an objective such as this, essentially what I showed you on the previous slide, but now I've inserted a representation of our data phi. So this is what we had from before, right? So think about it in terms of you have some representation, or you have some original space x1, x2, where the blue and the orange are somehow separate, but now we've moved to a new space phi where they are more identically distributed. But we also want to make sure that we can fit the data that we observe. So this was successful in domain adaptation, and it was used in the examples that I showed you before. This objective or algorithm has been used to get those kind of numbers on the benchmarks. But what we did was to essentially apply this to causal effect estimation as well. So we instead of having a single outcome, we now have two outcomes, right? We have an outcome for the control and an outcome for the treated. But we share a representation for these two predictions. So essentially what we do is we take our covariates, we learn a representation, and then depending on which treatment we did observe for every sample, we compute the loss in fitting that outcome either from the control or the treated. So if you're in the control group, you got a loss from the control hypothesis, etc. And what I'm not showing on this slide here is essentially this type of penalty that would be for the shared representation as well. So this is now fitting the factual data, but also penalizing differences between densities in the representation space. So it worked for domain adaptation. It turns out it works okay for causal effect estimation as well. This is a benchmark that's called the IHDP dataset, where your goal is to predict sort of learning outcomes for children based on facts about them and their mothers. And it has been synthesized. So the covariates are from a real-world dataset, but the outcome is completely synthetic. And we compare to a suite of different methods, but I don't know if we want to go too far into this table. These are methods based on various versions of the neuron net that I showed you before. But somewhat sort of disappointingly, the biggest gain that we saw from our work was essentially the choice of architecture. So doing regression well seems to do pretty well on this task. And this has been pushed far, like this number here is 0.67. We're kind of doing the ImageNet thing of optimizing to the test set at some point, I think. I don't think we should read too much into these numbers. But essentially, what I showed you in very early on, if you have ignorability and if you have overlap, doing regression well is all you need to do. So I think that's what's going on here. We see some sort of gain from this is using not the density difference penalty, not the DH term that I showed you before, but these three are. So we see some gains, but it's pretty minimal. It's essentially adding some regularization. Yep.
Can you just describe how high dimensional is the ISVP?
Oh, it's tiny. It's like 17 covariates or something like this, or 25 maybe. So that could be one reason. But I think, yeah. So if you take the MNIST examples from before, it's the same kind of. It's the domain adaptation algorithms are the same sort of family of algorithms. But again, MNIST is also kind of tiny. So people have applied it to bigger image classification tasks, but the causal effect estimation benchmarks are typically pretty small dimension. Yep.
When you're learning your standard picture representation there, it seems like so you're getting rid of differences that would help you predict the treatment assignment, right?
Mm-hmm.
If those variables, are you also assuming something about the homogeneity of the treatment effect?
No. So I think I'll answer that soon. So the question is, do I assume anything about the homogeneity of the treatment effect? Because I'm getting rid of information that could predict treatment, we got to kind of make sure that that's not predictive of the outcome, because then we lose the ignorability assumption. So I'll show that now, I hope. So this seems it seemed nice, like empirically, but we kind of have the luxury of hindsight for these tasks. So we like when it comes to the domain adaptation problems, we typically have the target labels and we can just see how well we did. But people have also chosen those tasks carefully. It's very easy to break them. And the reason that it's easy to break them is that this can obviously go wrong. I said that this was a bound, but it's not necessarily a bound for all phi. We had this assumption that the loss function or the loss of your hypothesis has to live in this family H, but the smaller you make phi, the less likely it is that it's true. And similarly, when I mentioned the triangle inequality version of this, where you have the realizability of the label in your hypothesis class, that also becomes much less likely, right, if you remove a lot of information. So ignorability need not hold for the representation, right? We kind of alluded to this a long time ago. But not only that, we may lose information in a sort of asymmetric way. If it's always true that the information that we remove is as useful for the factual as it is for the counterfactual, or for the treated as for the control, then this term will go up sort of the same way as this, right? So we have a shot that this bound still holds, even though this is even though the assumption of the loss being that is satisfied. Yeah, exactly, satisfied. But this can obviously go wrong. And I have I don't know if we'll have time to go through this in detail, but you can write a very tiny example for when it's impossible to solve the task in the way that we've solved it. Well, it's impossible to solve with any algorithm, in fact. So these are essentially your two domains, the gray and the white. So these would be your source and your target domain. And the circles and crosses illustrate the labels. And everything I want to show is essentially that if you pick either x1 or x2 as your representation, you will have a minimum density difference, because the gray and the white are sort of symmetric here, right? If you will have gray and white equally, regardless of the variable you pick. But only in one case can you perfectly separate the circles from the crosses. If I pick x1 as my representation, I will not be able to do that. So the thing is, of course, that there's no way for me to tell which of this is true, because I don't observe the labels on the target. So if the gray here is the target, it doesn't matter which I pick of x1 or x2. I can get perfect source classification, but not target classification. So this, yep.
So with regards to the problem you mentioned on the previous slide,
Yep.
I mean, the obvious solution would be to think about doing the bound that's not just taking supremum over all choices of f, but really of all choices of f composed with.
Exactly.
Now that bound might be too large for us to like or something, but
Yeah, so that's a very good question. So the bound that we wrote down and that doesn't hold, it doesn't hold because we didn't force it to hold for every phi, right? So it might not hold for a composition of a hypothesis and phi. And that is completely right. And that's the first easy fix. That's somewhat surprisingly missing from a lot of the papers doing this. The domain adaptation community has been a lot of empirical work for the last couple of years, at least a lot of it. But yeah, that's a good point. So yeah, I think I should move on a little bit. I think I might get to that question in a second. So another way to talk about this failure case is essentially considering predicting the effect of a drug, T. And we assume that this T has an adverse reaction or an adverse effect for some patients that could be allergic to some component in this drug. And the point is that this indicator for an allergic reaction, that we might know that a person is allergic to something, it will not be predictive of the outcome that we see in our observational data set, because doctors might not treat patients that have this property, right? So even if we observe this in our data, even if we have the indicator, we will throw it out if we do some variable selection or something like that. So this is an easy way this can go wrong. So another problem with existing domain adaptation methods, and I'll soon come to what we did. I realize I'm very short on time, but I think so anyway. But it's that the distances that you choose for comparing densities matter a lot. So this is kind of a stupid example, but what we're trying to do here is to learn from MNIST and generalize to MNIST, but a smaller version of MNIST. So we removed some of the labels, or classes, I should say. And I show you a few different lines here. This DANN is domain adversarial neural network, which is exactly what I was used to create the results on the benchmarks before. And what you can see here is as I remove digits, more and more classes from my target domain, this blue line gets worse. But what's perhaps more interesting is that this green line here has only trained on the source data. So actually, I think this should be, I'm a little surprised about this plot. But essentially what happens is that when you remove digits from the target domain, your density difference will be kind of artificially large. Even if you have all the labels or all the classes in your source, you have overlap completely, you have this difference between the densities that you will penalize in your representation learning algorithm. This red line here is illustrating what will happen if you you learn your representation based on this domain adversarial objective, but then you train on some labeled target data. So what it says essentially, we can recover a good classifier. So I haven't thrown away the information in some absolute sense. I haven't done variable selection here clearly, but so all hope is not lost in that sense. But of course, we don't have the target labels. And another way to look at these results is to say that these distance metrics, they penalize densities and differences in a way that we might not want to or expect. So these are two example tasks that we can consider. We have a source density, which is the blue one here, a target density, and you can see these have overlap everywhere. And we have a source and target here, and a lot of the distance metrics that are used consider this an easier task in the sense that the distance is, between these densities is smaller here. But again, like here we have shared support everywhere and we don't there, so we expect this to be an easier task in terms of extrapolation. So what we can do essentially is, what I've done in my work is to come up with a new representation learning bound that is not going to be, we don't have a shot of solving this always, this problem, because for the reasons that I showed before, it's impossible. But we've improved on a few things, I think. One of them is that we essentially do importance sampling when we can. If we have overlap, there's no reason for us to over-penalize the difference between densities. So in regions where we do have shared support, we revert to something close to importance sampling. In the regions where we don't, we still measure the difference in densities between learned representation, the density in the representation space, but we might lose on the realizability that we talked about before. So what this term measures here is essentially the difference between the label as a function of x and the difference and the label as a function of the new representation. So if you have an invertible representation, for example, this will be 0, that eta over there. And so that means that this holds for any representation, but you will have this term that you can observe at the end, the eta. So it kind of does a fix in the way that you suggested. We need a bound that's sensitive to the learned representation, but we are left with this problem that is impossible to solve, which is to say that there are terms in the bound that we can't observe. Now, something for us to work out is how does this behave when our representation is almost invertible. If I, for example, something that people have considered in practice is to add a penalty to your bound or to your objective, which says that you should be able to almost reconstruct your data from the learned representation. And then is that going to be close to 0? Well, that remains to be seen. So the takeaways from this part is essentially that domain adaptation can inspire for a causal effect estimation, I mean, they're in some sense mathematically equivalent, but if you think about the allergy example that I gave before, that's something that might hurt you more in causal effect estimation because you have this very biased way of introducing sort of non-overlap, right? A doctor probably knows about the things that might cause adverse effect, at least some of them. We have the same old problems that we did before in causal inference. We don't really gain much in terms of that, but at least we can think about like new algorithms or new ways of solving or estimating these effects. I think the idea of learning low-dimensional representation, or at least having low-dimensional representations, is crucial if you want to do if you want to ensure that you have overlap. So if you want to do weighting or matching or regression, you really want to work in a space that's sort of minimal, but also has the assumptions that you need. But in order to actually do this in practice, we need to figure out what are the right assumptions for that applies to a representation learning algorithm. Because there's, as I mentioned, there's no reason, unless you make it so, that the ignorability assumption or covariance shift assumption holds in your new learned space. But we also can't assume that we will have overlap in the original space, because most problems are high dimensional enough for that not to work. So I unfortunately don't have time to talk about the last topic of it today, but it's essentially, I can? Okay. Okay. The last, the last part, it will be kind of brief. But I mentioned early on that we have sequential problems as well, where we're interested in figuring out what is the value of some policy that produces an action given a state. So this is your typical reinforcement learning setup. And people have thought about applying this, and people have applied this to healthcare problems as well. So one of them I already mentioned, which is that of sepsis management. So, yep.
So before we get too deep into
Yeah.
this, can I ask one question about
Yeah, go ahead.
the stuff that you were describing
Absolutely.
previously? So one piece of information that you didn't lose is, that you didn't use is that
Mhm.
you said, okay, for some portion of the data, let's assume that I have overlap and I can do a good job
Yep.
using one of a variety of techniques
Yep.
in that section. And then you said, and then I know that I'm going to basically have to go out of, you can call it whatever you want, but basically
Sure.
to parts where I'm not identified.
Yep. Yep.
And then I'm going to have some loss associated with that, and
Yep.
have to basically trust that.
Yep.
So is there, what you didn't use there is any what I didn't hear is the information about the part where you actually do have identification.
Yep.
As a way of sort of doing a check on how bad you're doing for the part of the distribution that you're not using. So like, for example, let's say that you have a support that's like on the unit interval,
Mhm.
and for between 0.4 and 0.6 you have good overlap.
Yep.
And so that part you're dialed in. You can imagine sort of doing your best shot at like from 0.4 to 0.5,
Mhm.
using this algorithm across say like 0.5 to 0.8
Yep.
or something, and then
Ah.
using the information to validate how well the method is doing within the
Totally.
sample for which you're well identified.
Yeah.
And so that's like the one thing, I think that you're leveraging all of your data
Mhm.
and all of these identifying assumptions very well, but I was surprised that you
Mm-hmm. Yeah.
didn't describe that.
I think that's a very good point. So okay, short version of of that question, if I were to repeat it, essentially, why don't I use the knowledge I have of my fitting error in the regions where I do actually have overlap? Is that a
Basically.
okay? So I think that's a very good question. It's something I thought a little bit about. Essentially, this part here is completely insensitive to how well I'm currently doing, which seems stupid, right?
Well, I
In
don't
the
think it seems stupid, it just seems
well,
that,
it seems unnecessary. It seems wasteful.
yes.
Yes, I completely agree. So one way to think about that question is essentially, if we go back a little bit, I'm very happy you picked up on that. This supremum here is, you can think of that as the worst case loss. So we're taking a supremum over loss functions of your data, or on your data. But we know that most of these are not going to happen, right? We're only going to see the losses that are consistent with the loss that we already observed. That's fair? So you could write that down. The problem is that you have to figure out, how do I compute this thing for that kind of restriction? How do I make sure that I take the supremum only over things that are consistent with the error that I already observed? And I think if you're doing something like, there's a formulation of this where you're using essentially an adversarial loss, an adversarial network, for example. I think you have a better shot at doing it there than for what we've used here, which I didn't go into very much, but they're essentially kernel-based distances, like the maximum mean discrepancy. I think that restriction is tougher than for example, an adversarial network. So I think, that's a very interesting question.
I think there was a NIPS paper last year that did
Yep.
something similar to
Oh,
that.
cool.
We'll
We'll talk about it later. I'm very happy to hear it.
Sorry, if your data fit is coming through kernel regression, then it feels like it should just be, it should not be that bad in
Yeah.
terms of working with an undecided.
Wait, say that. Can you repeat that?
If the data fit that you did was
Mhm.
also like
Oh.
kernel regression fit, so that it's effectively an ellipsoidal
Yeah.
constraint, the supremum subject to an ellipsoid,
Yep.
then
I think that's fair. Yeah. So if you have a sort of kernel-based hypothesis that's to match this the discrepancy, it might be stream corporate constraint. I think that's true. thanks for that comment. Yes. So let's see. I think that's also interesting for the purpose of analyzing the domain adaptation example further, in the sense that in the ConvNet space that we use for these the classifiers, it is likely that the labels in the two different domains are not that far apart, or the images from the same labels, right? We were relying on some kind of closeness. If that wasn't true, we probably couldn't. First of all, we wouldn't get those results, but we also couldn't break it as easily as we did. Like we were relying on some kind of closeness like that, and having then this consistency constraint would be useful. Okay. So people have thought about reinforcement learning in healthcare, and in fact, there are a suite of papers that apply off-policy RL to exactly this problem, where your goal is essentially to manage well, a few different things. The simplest version of the problem that people have considered is dosing vasopressors, which is a drug that artificially increases the blood pressure of a patient. So what happens often is that a patient that has sepsis, or a lot of people in the ICU in general, have breathing failure and are put on mechanical ventilation, which means that they might have to be sedated to cope with the pain of intubation, which means that their blood pressure might go down. And then you have to artificially sort of tweak that. So what is the right dosage of vasopressors, and when should you take them off, because it can have long-lasting or long-term adverse effects? It's an interesting problem. Now, if you do this, or if you solve this problem, how should we evaluate the policies that we learn? Essentially, if we come up with something using off-policy RL, we will get some policy out, and we won't have to figure out, should we apply this in practice? And we have all the same problems that we had before. We have the overlap problem, we have the ignorability problem, but it's just much, much worse now. Because essentially what you could consider is the overlap between all of these different choices, right? Or if this is the policy that you might expect in practice, at least we want to know what happens close to this policy, right? But I know there's a lot of research on specifically this question. The goal that you're typically interested in is this value of the policy, which is just the expected long-term reward. I think I'll skip ahead a little bit, but you know essentially that this sort of overlap problem becomes worse and worse the longer my horizon is. And I've illustrated that here just by showing that if you were to do importance sampling in a setting like this, essentially what you're looking for is patients in the data that are treated exactly in the way that your proposed policy prescribes. And the further your horizon goes, this sort of group just gets smaller and smaller. So something called the effective sample size is exactly this. The number of people that you were left with at the end, even if this was your original sample. Recently I was involved in writing a sort of opinion paper on this, and there are a few problems, of course, that you run into that seem to have been glossed over in the literature in a lot of cases. So this paper was mostly a sort of warning sign, or sort of a warning rather, for these kinds of analyses. And we know that importance sampling has very high variance because of the importance sampling problem. It's also the case that some treatment regimes or some policies we cannot evaluate at all. We also have the problem that regression is often biased, and there's a lot of good work on trying to figure out how should we interpolate between these two different methods. The confounding problem is made worse in the sense that we have now confounding variables that are time dependent, so the choice of a medication later might depend on a choice that we made earlier. A very common thing is that you don't try the same thing twice if it didn't work the first time. And we have to deal with these kinds of things. But so this is something that has happened recently. People have looked at, or researchers that have published in prestigious places have considered various heuristic methods of evaluating policies. And I hope at this point in the talk you will sort of follow in my explanation of why this is not the right thing to do. And this is an example. Essentially what you have here on the x-axis or y-axis is the mortality of a patient in your data set, and on the x-axis is how different was the policy that we gave, or sorry, the action that we prescribed to that patient from what was in the data. And what they see is that, well, we have this kind of U shape here that says that if you're far away from our policy, then your mortality is higher. And you can see why this goes wrong, hopefully. That there's, this is by no means representative of any kind of causal effect, this difference between these averages here. So I should say, like, these have been binned in some ways, so you can take averages of patients, but it doesn't really solve the problem. This is no kind of causal effect, because what are the two interventions that I'm comparing here between these two groups? And is there anything that makes me believe that the patient groups that appear in this dot is comparable to this group here? No, these are completely different patients, right? Anyone who's treated like this is probably somewhat of an easy case, whereas here you could have patients that are very, very extreme cases. For example, one reason that you might have a lower than expected treatment in your data, or lower than expected dosage, might be that the patient, it's already too late. There's nothing we can do. And that we can't tell that from this plot at all. Or it might be that, or if you prescribe I'm not going to go on. You get the picture. So you can get the same figure. I mean, I didn't put the actual plot here, but you can get the same figure for a random policy. You can get the same figure for a constant policy in some cases. So this is purely an effect of the bias in your data, and not at all about the quality of the policy. So this was mostly to illustrate that this is something we had to think a lot about. I don't have a perfect solution for you by any means, but I thought that could be useful to see if you haven't already. The takeaway here is essentially that off-policy RL is only harder than the causal effect problem that I talked about before. Overlap is aggravated, and ignorability is harder to verify. So we have an opinion piece online on this if you want to read that. I haven't done any of this work alone, as I'm sure you've guessed at this point. I worked with these beautiful people, David, Rajesh, Uri, and Nathan, and this is me. And thank you for your attention. Yes.
One question, that's maybe more of a comment. Like, way back you made this comment that this struggle of learning a representation such that you get both ignorability as well as overlap is a sort of trade-off between the two. And I thought there was at least one example where that may not be true.
Okay.
I think about taking x's and like blowing it up to think about all possible interactions between the x's.
Okay.
Then it feels like that's maybe safer for ignorability, but whatever overlap was there before, there will remain that same amount of overlap. Like a deterministic blowing up of the x space. To think about all, like, take the polynomial kernel, for instance, right?
Sure.
So,
So you're not removing any information. Oh, yeah. That's fair. So another way to say that is that you might have, okay, so the question is if I artificially blow up my x by considering interaction, I might have a better shot at ignorability, but the same shot at overlap. That is true. So I mean, in some sense, you're talking about model misspecification there. If you consider any range of hypotheses, it doesn't matter, right? Like adding, if I can learn the interactions anyway, it doesn't really change the problem.
Yeah, so
if you see what I'm saying?
It depends on your hypothesis.
Yeah,
Because
it does.
If it was going to be linear, then it will matter
Yeah,
actually what
it does.
differences-
And I should say that a lot of work from the non-machine learning community has exactly that problem, but doesn't acknowledge it. So I think that's a very valid point. A reason that you might want to do that instead of what I suggest is that you might have some domain knowledge, just as some interactions are very useful, and then you get both a better sense of ignorability because you have some prior information, right? But you don't lose the overlap. So that happens a lot in practice, but it's typically when you have something like a linear model. Or no, okay, I thought you were.
I was, but I wasn't sure.
So what have you thought of, for the offline policy learning where you have
Yeah.
multiple treatments in the sepsis case?
Ah. Mhm.
Have you thought about what's the connection between that and the recent work by David Bly on the blessings of multiple treatments?
Ah.
Where
So is there a connection between the sequential treatment case and the blessing of multiple causes? I haven't thought about that. I think the blessing of multiple causes has the same issue in the sense that if you have more causes, you have less overlap still. And there's a nice blog post by a guy called Alexander Damour, who has thought a lot about the overlap question, where he argues essentially that the blessing of multiple causes is incompatible with overlap, in the sense that if we keep adding things that have some influence on the treatment, we're not going to have overlap the more we add, clearly. But we have to keep adding things to get the blessing of multiple causes, because their analysis is essentially taking the number of variables to the infinite limit. Anything there in between, I'm not I'm not sure. I haven't thought about that problem at all. But I think a typical sort of source of power for these kinds of things is where you observe the same kinds of interventions in different environments, as opposed to from the same density all the time. So think of it as having multiple source domains rather than multiple treatments, because you're looking for invariances essentially, right? So there's some nice work on that I think could be useful for that type of question. I don't know how exactly that relates to multiple causes.
And for the curse of dimensionality,
Mhm.
does it, I guess, philosophically, like, if I keep adding, so there's a question of like mathematical overlap in the
Yep.
population, and then there's, if I think about like the causal graph, and I think about the fact that probably the only variables that really matter that I have to confound for are the ones that seem to be not predictive, but causing
Yep.
the treatment assignment, right?
Yep.
And so, I guess I have a question about like how much does the curse of dimensionality matter in terms of the underlying dimensions of your space
Yep.
versus like the dimensionality of the number of causes of the
Yep.
treatment assignment.
So I think that's an excellent question. Essentially, the question is, does the curse of dimensionality matter for the variables that are not confounders? And no, you're completely right. In fact, for a lot of clinical tasks, what we observe is that something like deep learning doesn't add that much of a linear model, because the features that we've used are pretty well known and well understood, and they're collected for a reason. So something like a linear model works pretty well. What I mean, and the reason I say that is that not only do we do prediction well, but we also know more about the sort of causal structure typically in those situations. But when you have something like an X-ray image, it might be very difficult to reason about what are the pixels that matter. And so characterizing what part of the space I need overlap in is not so easy there. And the same could go for text, for example, text data, or I don't know if there's an audio data causal inference community, it could be. So I think, yeah, that problem kind of remains. What interests me a lot at the moment is you don't necessarily need to have the same confounders for every unit either, or every subject. What you need essentially is a minimal representation to predict your potential outcomes perfectly, and you need overlap in that space. But again, as you've seen, there's no way for us to identify that from data. You need domain knowledge for that. I think it would be useful to have a sort of shift in the way we talk about it, though, because this ignorability assumption is often just put out there as a sort of blanket statement. But what we need is to somehow incorporate the domain knowledge, right, to solve these problems. But again, how to do that? How to write down the assumptions for an image classification problem that it becomes kind of difficult sometimes. Yeah.
So I guess I was wondering, so I think it's kind of nice that you're doing these, like the way I was thinking about, so you present these bounds and how are they, how am I going to sort of use them? I'm going to use them because now instead of just maybe giving you a point estimate of this, what I think the treatment effect is, I'll maybe give you a confidence interval, of course, for first of all, having done a lot of bounds like that,
I know where you're
they're
going.
completely useless for anything you want to actually give out. But also, where I was thinking there might actually be a bigger utility is if I were to think about an iterative process, right? So maybe I like start with observational data, I do some fitting, but then maybe I can show like, look, these parts of space I have like really, really terrible fit in, and it would be very helpful if I could like go and acquire some data. Right? But now I feel like there is something kind of missing there, because it might be that, like again, if I think about let's say just thinking about a linear model, right?
Yep.
Then maybe there are a bunch of directions in which I have pretty good support,
Yep.
and then some directions in which I have pretty poor support. But if I just sort of orthogonalize that set of directions effectively and get some measurements, I'm done.
Mm-hmm.
Right? So in some sense, what I kind of, the question that's maybe missing is, if I were to think about now an adaptive strategy that to guide the next round of data collection, how do I sort of use these bounds to inform that?
Yeah, I think it's a very good question. So, like in some sense, okay, how do we use the bounds that I developed to guide data collection? Okay, there are several answers to this. One way I'm thinking about that is essentially how do we characterize overlap in general? Like we need some way to write down what are the people that we would like to observe if we could. And that's in some sense a problem on its own, but in some sense not. Like if you work only in the covariate space and forget about the label, you would typically you will have a more complex characterization than you might need, because you might say we have overlap nowhere. But as you also say, like if we have a very biased estimate of our label, we might get the wrong groups anyway. I don't have a perfect answer to this. I think what you brought up there with the linear model is interesting, because typically what will happen, right, if you have a linear model is that the fit in part of your space will influence the fit somewhere else. You will exactly, right? So having something flexible enough.
Thinking of all of this from again, like
yeah.
so when you were presenting the bounds, right? So you had specialized to a family of regression functions
yep.
and loss functions, and
yep.
so on, right? So now we have a well-defined problem in the sense that we can say, well, okay, first of all, I don't care about functions that like your guy mentioned.
Yeah.
I don't care about functions that have a bad model fit,
yep.
because they're just bad.
Yeah.
So now limiting to the functions that have good fit, what are the parts of the space that they are uncertain in?
Yep.
I would like to sample there, except like, again, because, I mean, if you're going to apply this, you know better than I do, if you're going to apply this in any kind of clinical or healthcare setting, your N is going to be pretty small.
Yep.
So in many settings that I apply in which are online, I could
yeah.
just say that, well, okay, I know roughly if I could for each data point have a sense of my uncertainty,
yep.
I could just decide and
totally.
I have enough data points that things will work out. But what you probably need is you need like 20 or 30 or 50 data points that will give you now the maximum coverage of all the
yep.
parts of the space where you're
so,
uncertain in.
So one way to think about that is that explaining the region of space where I do have overlap is in some sense harder than the opposite, because you need a high capacity model to say you need essentially the right model of the overlap to say to sort of conclude that we're good enough. But it's very easy to say it's sort of asymmetric. If you have a very simple model in which there is no overlap, then you know there's no overlap. But the reverse is not true.
It depends on what you're trying to certify, right? So I'm not trying to say that I will know the ground truth. I'm just trying to say, look, if I started that crappy family of models,
yeah.
I'm kind of stuck there, right? So I'm just trying to say, if you gave me, okay, so if you gave me data everywhere,
yep.
and I were to fit the best function from my class, which might be absolutely horrible.
Yeah,
so,
yeah.
But I just want to do as good a job as that.
Yeah.
Right?
Well,
so then I shouldn't need to worry about the high capacity part, should I?
Yes, in the sense that your horrible model might be too horrible to adjust for the confounding, so you might have bias in that sense.
I see.
When it comes to the overlap, it's slightly different. If you forget about the label, then I agree with you.
Yeah.
It's enough to have a crappy model as long as it can give me some information on where to look, but it will not give you a certificate for that you've looked hard enough. So it's kind of asymmetric like that. It will tell you don't have overlap, but it won't tell you you have overlap if you have two lines.
You have overlap with respect to that family of models, no?
Oh, so okay.
Right,
if you
right,
can,
so
okay. That's fair.
I define everything with respect to hypothesis class.
Okay, fair. So if you have some information or some idea that the truth is in that family or close to it anyway, then yes, that's completely right.
Okay.
Yeah. Thank you so much. It's a lot of fun.